For 9 through 12, they're just asking us to describe a transformation that's already been done for us. So here it comes down to some symmetry tricks, some visualization tricks, and possibly some memorized rules if the visual doesn't work as well. But the symmetry in number 9, I hope, is fairly obvious. That if I just folded along this horizontal line, those two triangles would match up. Since that involves folding around the line, that must have been a reflection across the line. So then we just have to name that line. Since it crosses the y-axis, but not the x-axis, that's simply the line y equals 2, and we're finished. For number 10, there's not a whole lot of symmetry here, really, so I don't see any way I could fold to get those two to match up, but I do see a rotation. I notice that point C hasn't gone anywhere to become C prime, so we must have rotated around that point, which you can just call C, or you can call it by its coordinates, 2, 3. So now we just need to know how much we rotated and in which direction. I notice that CB is horizontal, but to get to B prime it was vertical. So instead of a 180-degree rotation, this must be a 90-degree rotation. I also notice that B is up here, B prime is down there. So we must have rotated clockwise to get from B to B prime. Those labels are important here. That gives me all the information I need to know about a rotation. The center of rotation, the amount of rotation, and the direction, that this one was clockwise. Now number 11 is a little bit harder to see what's happening, and so this is a case where the coordinates will probably help more than anything. You might be able to tell exactly what's happened here, whether it's a reflection, a rotation, or some combination of those. But for most people, something like this, where they're not connected, it's harder to see. So like I said, I'll just use the coordinates. Point A has coordinates 5, 5, and A prime is at -5, -5. So I don't know if those two 5s, like if they swapped places. I know they both change signs, but that on its own doesn't give me enough to make a decision, so I'll just keep looking. Point B is at 4, 3. B prime is at -3, -4. This gives me a lot more information than the A and A prime did, because now I can tell both things that happened. The old x is the new y, the old y is the new x, and they both change signs. So our rule here is that they swapped places and they both changed signs. That happened for the a's as well. It was just harder to see that they had swapped places since they were both 5s. You could test that with point C and C prime as well and see that the same thing has happened. This rule we saw in an earlier question on the front. This is exactly what you get when you reflect across the line y equals -x. So that's the transformation that occurred here. That was based on the coordinates if you couldn't see what was happening. But we can also perhaps see what's happening kind of by connecting. I notice from C to C prime is a diagonal, B to B prime is a diagonal, A to A prime is another parallel guy. And if I just chop all those green segments in half, I end up exactly with the line y equals -x. But if you couldn't see that, the coordinates get you there just as easily. Number 12, I hope it's very clear that that's a dilation. Your triangle has gotten larger from ABC to A prime, B prime, C prime. So for a dilation, we need to know the center of dilation. And we also need to know the amount, or the scale factor, for the dilation. So, just like in number 10, I notice that this point hasn't changed, so that must have been the center of dilation for number 12. You can call it point A, you can call it by the ordered pair, you can do both, it doesn't matter. So then we need a scale factor. To determine that, any transformation, any dilation specifically, should do the same thing to all of these points and to all of the sides. So I'm just going to choose a side that's easy to work with. BC is horizontal, so I know exactly how long it is. It's 2 units long. B prime C prime, of course, is also horizontal, so I can tell easily that it's 6 units long. So the new length, B prime C prime, was 6, but the original length for that side was just 2. Hopefully, you know that you would have to multiply by 3 to turn a 6 into, to turn a 2 into a 6. But if the numbers aren't quite as easy as they are here, remember you always have the trick new over old, which in this case is 6 over 2, which is a scale factor of 3. But we just needed to turn the old length of 2 times something to get a new length of 6. And mentally we know that that something must be 3. The rest of these are talking about some other things that we've dealt with during this unit. So 13 and 14, we're trying to map a triangle onto itself, which just means that after we apply the transformation, we end up with an identical picture. So let's just take a look at each of these 4 options, see which ones work. So 180 degrees around 3, 3, which is this point right here. If I go 180 degrees around that point, we're going to be in the exact opposite position. So, for example, instead of moving down into the left to get here, move up and to the right, which was not a vertex of our original triangle, so this one is out. Okay. Reflecting across the line, y equals x. That has a slope of positive 1, so it goes uphill from left to right. And you can see that that pink line is a line of symmetry. If I folded along that pink line, then this distance would transfer to that distance. This vertical piece would fold onto that horizontal piece, and everything would match up. There is symmetry across this line, so a reflection across that line would work. It would get the triangle to map onto itself. 360 degrees, I don't even have to keep looking. If I rotate anything 360 degrees around any point, it's going to match up with itself. That has nothing to do with this picture or that point, just the 360 degree rotation. So that one's pretty straightforward. And then, reflecting across the line, x equals 3. So we cross the x-axis at 3, and then we go perpendicular to the x-axis. You can see that orange line is not a line of symmetry. This point up here would end up landing right there, which was not a vertex of the original triangle, so this one's a no. So a 360 degree rotation, of course, gets anything to map onto itself, and because of the symmetry of this triangle, a reflection across y equals x works as well. 14 is basically the same idea, just asking us to describe how to get it to line up with itself or map onto itself. So, a reflection across the line y equals something. Well, let's just look at the reflections that work. I see symmetry here for this rectangle along this line, and I see symmetry along that line. So we just need to decide which of those matches which of these equations. My blue line crosses the y-axis at -1, and then it's perpendicular to the y-axis. So my blue line is the line y equals -1. My red line crosses the x-axis at 3, and it's perpendicular to the x-axis. So that's the line x equals 3. For part C, as we saw in the previous question, there actually are several correct answers here. One way to answer part C would be just to say rotate 360 degrees around any point that you want. We saw that in number 13. A 360-degree rotation will, of course, map something onto itself because it's a full rotation all the way around. Here, let's try to be a little bit fancier than that. Get a slightly better answer, more specific answer for this rectangle. So here, a 90-degree rotation is going to take this tall rectangle and turn it into a wide rectangle. I don't want that to happen. It wouldn't map onto itself. So this must be either a 360-degree rotation, as we talked about, or perhaps just 180 degrees. So then we just need the center of the rectangle, which we've kind of already drawn, as the spot where those two lines of symmetry meet. 3, -1. If I rotate 180 degrees, this point in the upper right corner of the rectangle would end up in the lower left corner, and vice versa. So 360 degrees around any point would be correct. But for this rectangle specifically, 180 degrees around its center is a little bit more specific to this rectangle, so we'll go with that. Okay. For number 15, we're applying two transformations, and then in part B, they're going to ask us to come up with a single transformation. We saw that in one of the questions on the front, but here they're specifically asking us to describe a single transformation. Okay. So let's reflect across the x-axis. Give me just a second. So going across the x-axis, we've done that a couple times already on this sheet, either through the graph or through a memorized rule. Point C is 1 unit above, so we'll go 1 unit below. B is 2 units above, go 2 units below. Then A is 4 units above, go 4 units below. So that gives me A prime, B prime, and C prime. Then they also asked me to translate that new triangle up 2 units. So B prime moves up, there's B double prime. A prime moves up, say double prime, C prime moves up, and actually lands where C was originally. So that blue triangle is my final answer. It's the only thing you have to draw. And then coming up with a single transformation that would have done the same thing. We did it through 2 steps, but we could have done it through 1. You can see on here some symmetry between the black triangle and the blue triangle. If I folded along this line, those 2 triangles would match up. Folding tells me it's a reflection. So if we had reflected that original triangle across the green line, we'd be good to go. That green line crosses the y-axis at 1, but never crosses the x-axis. So that's our line. 16, pretty much the same thing. In fact, it's almost exactly the same thing, but in reverse order. So let's see if that gives us the same result. This is telling us to first do the translation. So triangle ABC moves up 2. There's A prime, B prime, C prime. And then we take that blue triangle and then we'll do the reflection across the x-axis. B prime is 4 units above the red, so we'll go 4 units below for B double prime. C prime is 3 units above, with 3 units below. And A prime is all the way at the top, 6 units above, way at the bottom, 6 units below. And there, in red this time, is my final answer. So you'll notice that those two are, of course, different, 15 and 16. The order of the transformations did make a difference. But it's still a reflection. To get from the black triangle to the red triangle, there's some symmetry. Those are 4 units apart, C and C double prime. So halfway, that gives me the axis of reflection, the line of reflection. So we're reflecting across that green line, but this green line crosses the y-axis at -1. So we have the line y equals -1. So again, just notice that those two are different because the order changed, and that's all it took to make the process quite different. That finishes it up for the transformations problems for the EOCT review, and we have these videos for all of the units that you'll see during this review session.